So before going to the main technical session, I would like to tell brief you about IASTA. I'm Arshad Khan, who is a member of Executive Committee of IASTA. This organization or association, Indian Aerosol Science and Technology Association, it was founded in 1988 to promote and exchange science, knowledge of technology and knowledge of technology, aerosol technology between industry and academia in 1998 in Mumbai with 10 founding members. So this organization also, with this new committee, we have started online monthly series of lecture series with distinguished speakers. So this one is 4th online meeting by IASTA. Apart from this, we also carry out IASTA conferences. So for this year, we are going to organize this meeting in Mumbai at Hotel Vivanta during 12 to 14 December 2023. And this flyer is also out for this meeting. Last date for submission of this meeting is 31st. 31st December, the last date for submission of paper is 31st August. So I request all the members to submit the paper fast. I know this one is, we are doing it very early, but we do not have time and we need to submit the paper fast. So with that information, I would like Dr. Padma to take over and introduce our distinguished speaker for this technical session. Over to Dr. Padma, please.
Thank you, Dr. Arshad Khan. A very good evening to all. I once again welcome you all to this 4th monthly online lecture series of IASTA. And it gives me very immense pleasure to introduce our today's distinguished speaker, Dr. R. Krishnan, Director, Indian Institute of Tropical Meteorology, Pune. Dr. Krishnan is a highly renowned climate scientist. He specializes in climate modeling to understand scientific issues relating to climate change, Asian monsoon, and water cycle. Under his leadership, the Center for Climate Change Research, CCCR at IITM, Pune, developed the first Earth System Model, ESM, from India that contributed to the CMIP-6 and IPCC-6 assessment report. He was a coordinating lead author in the IPCC AR6 WG1 report and also a drafting author in the summary for policymakers. He was also a coordinating lead author of the Hindu-Kush Himalayan Monitoring and Assessment Program, HIMAP. He is a member of many committees, national and international committees. He is a member of Joint Scientific Committee, JSC, World Climate Research Program, WCRP, and also World Meteorological Organization. He and his team from CCCR IITM published the first National Climate Change Assessment Report of the Ministry of Earth Sciences, Government of India in 2020. After obtaining MSc degree in Applied Mathematics from Madras Institute of Technology, Chennai, he pursued PhD research in atmospheric sciences at PRL Ahmedabad. He was awarded PhD degree from University of Pune in 1994. Before joining IITM as a senior scientist in 1995, he was a research fellow at PRL Ahmedabad and a senior scientific officer at NCMR-WF New Delhi. From 2011 to 2022, he was an executive director for Center for Climate Change Research, CCCR at IITM. And during this period, he also served as an acting director to IITM thrice and became director IITM from June 2022. He has published over 152 scientific articles or research papers and co-supervised over 14 PhD degrees and 2 submitted and 8 ongoing. He is the recipient of many awards, honors, and recognition. A few of them are National Award for Excellence in Atmospheric Science and Technology 2021 from Ministry of Earth Sciences, Government of India, and Fellow of Indian National Science Academy, New Delhi 2020, Fellow of Indian Academy of Sciences, Bangalore 2017, Fellow of India Meteorological Society, India 2017. He is the recipient of IITM Golden Jubilee Biannual Award for Outstanding Research Contributions in 2014. And he is also a recipient of IITM Silver Jubilee Award 5 times for Best Research Papers. And he is the recipient of Professor Anand Varnekar Award from India Meteorological Society. He is also a member of several national and international committees, editor for Monsoon, Journal of Indian Society of Remote Sensing, Earth System Dynamics from 2015 to 2020. With this brief introduction, I now invite Dr. Krishnan to deliver his talk on this very important topic, understanding regional monsoon precipitation response to global climate change. Yes.
Yeah. Thank you very much, Dr. Padma, for the very nice introduction. And also many thanks to Dr. Neeraj Rastogi, IASTA, and so many senior people who are there today participating, Professor Devra, Professor V.B. Rao, and many of my friends and colleagues at IITM. So thank you all for this opportunity. And so let me go to share my presentation. So are you able to see the screen? No?
Not yet, sir.
Okay. Okay. Just a minute.
Yes, sir. We can see now.
Can see it now?
Yeah. Maybe
Okay.
we can go to full screen mode. Yeah. Okay. Fine.
Yeah,
Fine.
great. Yeah. So, so today's talk, when Dr. Neeraj asked me to give this talk for IASTA, I was thinking what I can really talk on, because aerosol is a very important player in when we talk about climate, and also it's becoming important for weather. But my expertise is actually in the monsoons and climate change and water cycle. So I took some time, and maybe I thought I should talk about the changes in the monsoon precipitation that are happening in a changing climate, in a globally changing climate, and how we can understand the regional, when we talk about monsoons on a regional scale, how they are, because monsoon is also a part of the water cycle, an important component of the water cycle. And so how question is climate change is happening, there are different drivers. It's not only the greenhouse gases, but also the radiative effects of these aerosols, which are suspended particles in the atmosphere. They can be produced naturally. They can also be produced due to human activities. And what is their influence on the monsoon precipitation? So keeping that view in mind, I thought I will talk on this regional monsoon precipitation response to global climate change, how we can understand that. And basically, I will be talking about the IPCC assessments that came out from the last assessment report. So I think this is, yeah. So this is one of from the summary for policymakers, it says, human influence has warmed the climate at a rate that is unprecedented in the last 2000 years, that we have the observations from the paleo records, from the model simulations. So this rate of warming is unprecedented. It is mainly because of the human activities. That is also we very clearly know. And this is probably the warmest multi-century period is in more than 100,000 years. And also when we talk about changes in the global temperature, this is again from the CNIP 6 models. We have the black line is the observed temperature change time series. We can, and the brown line is the experiment with natural and anthropogenic drivers. So clearly, this warming trend that we are seeing can be explained only when we have the. I think there's a call just coming 1 minute. Hello. Hello.
Hello.
Hello. I'm sorry, I'm on a talk. Sorry. So the increasing trend cannot be explained only by natural factors. And more importantly, when we see the natural, when we have only the natural forcing like the solar irradiance changes or the volcanic eruptions, which throw a lot of stratospheric aerosols into the stratosphere, you can also see these episodes like the cooling episodes, like the Pinatubo that you can see, and also the El Chichon and some of these events where the global temperatures cooled. But this overall warming trend that we see is mainly coming because of the effect of the greenhouse gases largely. And as I said, it is not only the greenhouse gases, there are different drivers, anthropogenic drivers, especially the aerosols. And one more statement is that the observed warming is driven by emissions from human activities with greenhouse gases warming, which is partly masked by aerosol cooling. So what we showed was the present warming level of warming is around 1.15 degrees. And if we had only greenhouse gases, the global mean temperature would have increased by 1.5 degrees. This is again from the CMIP model, CMIP 6 models. So basically, the other human drivers have led to a cooling of about close to minus 0.4. And especially sulfur dioxide, SO2 itself would have cooled about 0.5 degrees. There's a net cooling because of this. And also other aerosols, a slight cooling from organic aerosols, and also land use irrigation changes, and also nitrogen oxides. So, but mostly the warming is coming from the greenhouse gases, and aerosols have produced a significant cooling, at least during the historical period. And so in the future, these are some of the changes in the temperature in the future. The assessment says global surface temperature will continue to increase until the mid-century under all emission scenarios considered. And global warming of 1.5 degrees and 2 degrees will be exceeded during the 21st century unless deep reductions in carbon dioxide and other greenhouse gas emissions occur in the coming decades. So we are going to exceed the 1.5 degree in the next 15-20 years. And the SSP 245 is a kind of the middle of the road scenario where we will even cross the 2 degree warming by end of this century. And greenhouse gases, they have a long lifetime, they're going to be there. And so the temperatures are going to increase. And also the assessment is that there was a very strong regional attribution in the ER 6th assessment report, which said that with every increment of global warming, changes will get larger in regional mean temperature, precipitation, and soil moisture. So presently we have, this is the observed change presently at 1 degree global warming. And this is what is simulated by the models on the right-hand side. You can see much of the maximum warming is happening in the polar and the high latitudes, which the models are able to capture. And the rate of warming is reduced, is lower in the tropics and equatorial areas. So with at the 1.5 degree and 2 degree, and as the warming level, global warming level increases, we can see that globally the pattern of warming also getting magnified with increased warming at the polar regions and the high latitudes. Also other areas, the warming signal becomes very prominent in the future. And also not only the temperature changes, when you look at the precipitation changes, the high latitude and the mid latitude with increased warming, precipitation is going to increase, is all again from the CMIP 6 models. And some of the monsoon areas over South Asia, West Africa, precipitation is going to increase over this region in the future with warming levels. Whereas some of the dry areas in the Mediterranean, the subtropics, they are going to get drier. So it's like the wet is going to get wetter, wet regions, and dry regions are going to get drier. Which also means that some of these dry areas, the aridity, the soil moisture will decrease because of more evaporative demand from the soil. So the soil moisture will decrease, which means more aridity will increase in these areas with higher warming levels. But some areas, the aridity, there's going to be increased soil moisture because of the precipitation, increased precipitation. So, as I said, I was involved with the water cycle chapter. This was for the first time the IPCC had a dedicated chapter on water cycle. And we had a section on the theoretical basis. When climate change happens, what is the theoretical basis for which we can expect water cycle changes? And we had a section on the observed changes. What are the actual changes that have been observed? And what are the future changes in the water cycle? And also we talked about the internal variability, the non-linearities, and what are the uncertainties in the water cycle changes in section 8.5. And abrupt changes was also discussed in section 8.6, potential abrupt changes and final remarks. And when we go to the quick guide, we discussed different components of the water cycle, the evapotranspiration, global water cycle intensity, intertropical convergence zone, tropical rain belts. We had also a dedicated focus on the monsoons, this in the chapter 8, which is also a component of the water cycle. Precipitation, runoff, stream flow, flooding, soil moisture, aridity and droughts, water vapor and its transport. And we had also some boxes where we discussed about the role of aerosols, changes in seasonality and so on. So we recognize that aerosols are very important for the water cycle changes. I'll be talking about this. And now, as I said, monsoon was a special focus in the water cycle chapter. And we had different regional monsoons. And I'm just showing the Indian monsoon or the South Asian monsoon, which is among the strongest among the regional monsoon systems, among all the regional monsoon systems, because of the strong seasonal wind reversals and the strong seasonality of the precipitation. And so this is actually the Indian monsoon is this is to show that it is really a complex dynamical system. The complexity coming because of this distribution of the land ocean in this region, the contrast land ocean contrast. You have the elevated Tibetan plateau, the Himalayas in this region, and then the oceanic areas. And then because of this thermal contrast that is set up during the pre-monsoon and early monsoon season, which leads to the development of the pressure gradient and the winds. And also this is the region where the equatorial ocean atmosphere dynamics becomes very strong, because to the south of the equator, you have the Coriolis effect trying to deflect the wind to the left. And as it crosses the equator, the flow is again deflected to the right. And then as the wind blows over the oceanic areas, there is evaporation, it picks up the moisture. You have the formation of the clouds, different types of cloud systems. And as the water vapor condenses in these deep clouds, it is also going to produce huge amount of latent heat of condensation, which in turn acts to feedback as a positive feedback on the winds. So there is a constant interaction between the clouds and the heating and the winds and the precipitation. And it also affects, because of this interaction of these winds with the East African mountains and the adjoining oceanic areas, you can have upwelling, increased oceanic upwelling that brings all the nutrients and primary productivity to the surface. So it's also a biological, it's coupled, even the biological system is coupled to this land atmosphere ocean coupled system. And the equatorial dynamics is very, very important, especially in this region for the monsoons. And we also have this very nice distribution of mountains, the East African highland mountains to the south and north of the equator, which play an important role in setting up these meridional winds off the coast of East Africa. And this boundary layer is very deep. So these winds can extend very more than 2 to 3 kilometers. And so the boundary layer processes become very important. And these mountains also have an important role in the acceleration of the Somali jet. Not going into these details. And so this was a paper by Rodwell and Hoskins, where they show the region of the PV as the air crosses to the north of the equator. It attains a positive PV, potential vorticity. And this is the negative PV line, and this is the zero PV. And so this change of PV as the air crosses from the south to the south of equator to the north is very important for maintaining the cross-equatorial flow and the Somali jet. And the East African highlands have a very, very important role. If you did not have these East African mountains, the Somali jet would not intensify. And so PV modification is very important and for the maintenance of jet. So this is just to highlight that this is a very complex region, the Indian region, South Asian monsoon region. And of course, the rainfall, the seasonal rainfall, this is the distribution of the mean rainfall, is spatially not uniform. Everybody knows about it. You have heavy regions concentrated along the Western Ghats and the Northeast India, and also considerable rainfall over the core monsoon region of central and eastern part of India in the north. And of course, the monsoon rainfall is subjected to intra-annual variations. And many of the wet monsoons and dry monsoons in the past were associated with wet events during La Nina years and dry monsoons mostly during El Nino years. And also, of course, there are some years where wet and dry monsoons have happened even in the absence of El Nino. And this paper was an analysis of the links of the monsoon rainfall with the sea surface temperature variations globally. So by a maximum covariance analysis was by Vimal Mishra et al. They showed this analysis of rainfall and the sea surface temperature linkage. The first mode in the rainfall, which shows a decreased rainfall over India, is associated largely with the El Nino-like pattern with warming in the central and eastern Pacific and cooling in the west. The second mode is associated with the warming where it is more like a break-like pattern of decreased rainfall over the plains of the Indo-Gangetic plains, associated with warming in the Indian equatorial and tropical Indian Ocean. So clearly, sea surface temperature variations are very important for the intra-annual variations of the monsoon. And another important discovery was the IOD by Saji et al. In 1999. It's an important mode of variability in the Indian Ocean, just like the ENSO in the Pacific. And it turns out that this mode is a coupled variability of the atmosphere and ocean, coupled variability in the Indian Ocean. And it turns out that many of the positive IOD years, where you have more cooling of the sea surface temperature in the Eastern Indian Ocean and anomalous warming in the West, these like examples like 94, also 97 was also El Nino IOD year, positive IOD year, 1961, 2019. They were all associated with stronger than monsoon rainfall over India, and with enhanced because of the suppressed because of the cold sea surface temperature anomalies in the Eastern Indian Ocean and high pressure anomalies sitting, rainfall over the Eastern Indian Ocean was subdued, and because of the high pressure, there was an outflow from the lower level, outflow of moisture, which was then transported. The moisture was in turn transported by the cross-equatorial flow, which was converged later, which later converges over the monsoon trough region and produce heavy rainfall over the parts of North India, Gujarat, even Northwest India, Gujarat, and other adjoining areas. So the IOD is an important driver as well. And so why I am highlighting this is the latest plot of sea surface temperatures for 2023. And you can see that we are in the midst of an El Nino, a very strong El Nino with warming in the Eastern Indian Ocean. And the monsoon rainfall as over India, initially it was a kind of a lull until the first half of June, and in the later part of June, since then the monsoon has been picking up, and we are now more than 7% of normal all India, and many parts in India are wet. There are also dry areas. All India as a whole, I think it's more than 7%, plus 7%. Interestingly, it turns out that we are seeing cold sea surface temperature anomalies in the southeastern Indian Ocean. We don't know if this is going to turn out to be an IOD year this year as well. Let's wait and watch. So, and some models have indicated that this will be a positive IOD year as well. So there are these different drivers of sea surface temperature influencing the monsoon precipitation. And also when we talk about the monsoon within this region, it involves multiple scales. We have rainfall. This is a picture by Rao, which shows the region. These hatched areas are where rainfall is more than seasonal rainfall exceeds 100 centimeters. So it can come by a variety of processes through these low pressure systems that form in the Bay of Bengal, depressions, which move westward and produce, the synoptic systems produce a lot of rainfall. Also, you have organized convection extending for several thousand kilometers. I'll show you some pictures. And you have this movement of this convection rain bands, which cause this active and break monsoon spells. So these are happening on a much low frequency time scale. They have longer time scales compared to the synoptic systems, which are a few days. And you have a very large scale monsoon, which is set up by this north-south gradient. So these are different scales, both in temporally and spatially. And these produce the rainfall. The net result is what we see in the form of a rainfall. And they're all interacting. And you also have phenomena like the mid-tropospheric cyclones, which can give a huge amount of rainfall over Gujarat and areas in coastal Maharashtra. I'll come to that. And so on top of that, you have now the climate change. As I said in the beginning, you have different drivers like the greenhouse gases and aerosols, the two prominent ones. And they have also affected the temperature and precipitation globally and also over the monsoon region. Again, this is a paper by Bonfields et al. This is based on the CMIP-5 models. They analyzed what is the fingerprint of the greenhouse gases on the temperature and on the precipitation. So generally the warming signal, you can see the greenhouse gas warming prominently in the temperature fingerprint, and the precipitation fingerprint of the GHG, you can see increased precipitation, mid-latitude, high latitude, and some areas in the tropical oceanic areas, and also the monsoon region. Whereas the dry areas, the subtropical areas, you tend to get reduced rainfall in these areas because of the stronger Hadley circulation, more stronger descent in the subtropics. But when you look at the aerosol fingerprint in the temperature, aerosol, mostly these are, when we are talking, these are the anthropogenic aerosol emissions. Mostly the sulfate, as I said, globally, they have contributed something like 0.5 degree cooling, 0.4, 0.5 degree cooling. Much of these emissions dominated in the northern hemispheric regions of America, Europe, China, and other areas. And they have led to a cooling mostly in the northern hemispheric continental areas and compared to the southern hemisphere. So the aerosol fingerprint tries to produce a kind of interhemispheric asymmetry with more cooling in the northern hemisphere. And because of this cooling of one hemisphere due to the aerosols compared to the other hemisphere, there are theoretical explanations which suggest that the ITCZ should shift to the warmer hemisphere. So when we look at the precipitation fingerprint of the aerosol, we see that there is increased precipitation to the south of the equator. And whereas the areas to the north, there is reduced precipitation, including India, West Africa, and many of these monsoon areas. So typical aerosol fingerprint is try to shift the rainfall and the ITCZ to the warming hemisphere. And we also see the signals in the soil moisture and in the aridity fingerprints of both the greenhouse gases and aerosols. So you can see this picture, the greenhouse gas emissions have continuously been rising from in the observations. The aerosols, mainly the sulfate emissions in the mid-latitudes. This is the axis is going down on the downwards on the y-axis. You can see the aerosol emissions primarily increase in 60s, 70s, and 80s. And later on in the 90s, there were some aerosol regulation norms. I'll come to that, especially in North America and Europe. And this has improved the quality, air quality to some extent. And we also see while the greenhouse gas forcing continued, there were some improvements in the aerosol emissions in these regions. And that have led to some changes in precipitation, especially over the West African monsoon region. I will come to that. And so this is the assessment of the global and regional monsoon changes, both in the historical and the future. So the global monsoon, this was earlier defined in the 5th assessment report, basically by Bin Wang and a group of people who argued that the global monsoon is defined as the area where the local summer minus winter precipitation rate exceeds 2.5 millimeter per day. And the global monsoon domain is shown by this black line. It covers both land and oceanic areas. And they also included many areas, these dotted areas, which we see over Equatorial America and South America. It was part of the global monsoon. But in the 6th assessment report, we are mainly focusing on the regional monsoons, which are defined based on the published literature and based on the expert judgment from the different regions. And the dotted areas which are shown over South Africa and Equatorial America, we don't call them as monsoon regions, because in these regions there are seasonal variations due to the movement of the ITCZ and the rain belts. But whether it can be qualified as a monsoon region is a matter of debate. So that we have restricted to only the 6 monsoon regions over South and Southeast Asia, the East Asian monsoon region, the Australia maritime continent, West Africa, North America, and South America. And the assessment is that the global land monsoon precipitation decreased from the 50s to the 80s, partly because of the anthropogenic aerosols, but has increased since after the 80s in response to greenhouse gas forcing and large-scale multi-decadal variability. This is, you have to keep in mind, because the GHG forcing dominated in the later part. So there has been a recovery of the rainfall, and also not only the GHG, also the multi-decadal variations in the system. And so during the 21st century, global land monsoon precipitation is projected to increase because the greenhouse gases have a long lifetime. They are going to continue in response to the GHG warming in all time horizons and scenarios. This is a high confidence. And also when we look at the distribution of the rainfall changes in the future, the African and Asian monsoon are going to be increased, get stronger compared to the North American monsoon. So there is going to be enhanced east-west asymmetry between the monsoon regions. The West African monsoon and Asian monsoons are going to intensify in the future. And so that is a short assessment, and this was all based on the CMIP6 model and the observations. This picture shows the trend and change in precipitation 51 to 2014. This is the observations past for South and Southeast Asia on the left panel and East Asia. And we have the CMIP6, we have 3 different data sets here, the Aphrodite, CRU, and the GPCC. The trends are shown from 3 precipitation data sets, the region I showed in the previous map. And we have the all forcing experiment from the CMIP6 models, the natural only, which had only natural forcing, the aerosol forcing experiment alone, and the GHG forcing experiment alone. So clearly the contrasting signatures of the GHG and the aerosol forcing on the precipitation can be seen over the East and South Asian monsoon regions. And clearly the all forcing experiment shows that there's a decreasing trend when we have both these drivers. And in fact, the observed trends also show that precipitation during this period decreased. And we see a similar scenario in the East Asia. And in the future, for the South Asia and East Asia, we have the near term, that is 2021 to 2040, midterm 2041 to 2060, long term is 2081 to 2100. And we have 3 different scenarios, the 126, which is a kind of a low emission scenario, and then the medium scenario, that is SSP 245, and the SSP 585 is a high emission scenario. So as the magnitude of warming increases from the high emission to the low emission scenarios, the precipitation, monsoon precipitation is clearly projected to increase also into the future as the greenhouse gas warming levels are increasing. In future, we expect more precipitation and also increased variability. And when we look at I wanted to draw your attention to the changes in the northern hemispheric shortwave radiation. This is based on the GBA data set, which is mostly available in many parts of the mid-latitudes, Europe and North America. What it shows is the summer shortwave radiation in many of these, from the 70s, especially up to the 90s, this shortwave radiation decreased at the surface very clearly. And this is because of the effect of the anthropogenic aerosols. Emissions increased, And due to the scattering and the absorption of the radiation, mostly the scattering effect, there was a decrease in the shortwave radiation. And you can see that the all-forcing experiment from the CMIP6 models and also the aerosol-only experiment show this reduction in the shortwave radiation. Although the amplitude is much weaker, you don't get this very. And thereafter, due to the, as I said, due to the improved emission norms, there was a recovery in the shortwave radiation because of the reduction in the aerosol emissions. There has been this recovery, and the models do this to some extent, but they underestimate this variability, this decadal variability. And when we look at the northern hemispheric summer precipitation, this was described by a paper by Polson et al. They call this as the northern hemispheric land summer precipitation, and that decreased. So the precipitation, observed precipitation from the GPCC is shown by this black line, also the CRU data set. And we have the all-forcing experiment, which is shown by the red line, and the orange is the GHG only experiment, and the aerosol experiment is blue line. Clearly, you can see that associated with the decrease in the solar radiation in the northern hemisphere, there is a decrease in the summer monsoon precipitation in the northern hemispheric summer. So again, this is also supported by the model, CMIP6 models. So clearly, the aerosol has been an important driver, and we also see this decadal variability in the signal, which is somewhat underestimated in the models. And so over West Africa, especially the effect of the decadal change, the decrease in the precipitation during the 80s, and the recovery, later part as the GHG increased, whereas the European emissions of the aerosols and the North American aerosols, the emissions were improved. You can see there was a recovery in the monsoon precipitation over West Africa, especially. And in the future, as we reduce the aerosol emissions and the greenhouse gases continue to increase in the future, and the West African monsoon precipitation is projected to increase in all the scenarios. So the point is, there have been different drivers. It is not only the greenhouse gases. When we talk about precipitation, monsoons, we have to keep in mind there are these aerosol become an important driver changes. So in short, for the Asian monsoon, the South and Southeast Asian monsoon precipitation decreased since the mid-20th century, the dominant cause being the anthropogenic aerosol forcing. And the dry South and wet North pattern over East Asian summer monsoon precipitation change results from the combined effect of greenhouse gases and aerosols, high confidence. In the near term, South and Southeast Asian monsoon and East Asian monsoon precipitation will be dominated by the effects of internal variability. So this is something very, very important. I will come to this when we talk about internal variability. That is in the near term, we have to also keep in mind the role of volcanic eruptions, which are very, very important. And but in the long term, it will increase because of the greenhouse gas forcing. That is the later part. This is a medium confidence statement. And so, as I said, internal variability is an important issue. And there are various uncertainties when we talk about the projections of the regional precipitation, monsoon precipitation changes. So there are different sources of uncertainties which was assessed. It can come because of the model response uncertainty. There's if you take multiple models, among the models, there's a large spread, intermodal spread among the climate models. And this spread is an intermodal spread is a source of uncertainty. Also, the physical processes in the models, they're parameterized. It could be convection, it could be aerosol microphysics, clouds and precipitation, land surface processes. So we, at the subgrid scale, we don't understand, but they have to be parameterized in these models. And that is also, there are uncertainties resulting from that in the representation of physical processes. High resolution models provide some value addition. It could be convection permitting models and so on. But even those models also come with uncertainties. But in addition to the model uncertainty, there could be internal variability. This is an important point. For internal variabilities, for example, changes in the decadal timescales in the ENSO, Pacific Decadal Oscillation, and also volcanic forcings. In the coming decades, there could be big volcanic eruptions. These are all natural forcings, and these internal natural forcing is a source of uncertainty, can introduce a lot of aerosols in the stratosphere, and how it is going to affect the monsoon, we don't know. That is a source of uncertainty. And also there are non-linearities across the warming levels, because the non-linearities can occur because of the changes in the circulation and precipitation, which we don't understand, and land surface process and feedbacks, which there are many non-linearities due to runoff, groundwater recharge, snow melt, soil moisture, evapotranspiration, and so on. And there is a potential for abrupt changes. Recently, in the last few days, you can see that there's a paper that saying that the AMOC, the Atlantic Meridional Overturning Circulation, it's showing some weakening signals. They're telling it could collapse, but that is of course, the IPCC AR6 assessment says the AMOC collapse is unlikely, very unlikely, but there is a potential for those abrupt changes. And also there are changes due to the Amazon deforestation and greening of the Sahara and Sahel. So these are all abrupt changes it can introduce in the water cycle changes. And there are also changes in the scenarios. I showed the low emission, mid emission, and high emission, but the scenarios itself could have uncertainties. They could have scenario uncertainties. So I'll not get into all these uncertainties. I will focus on the internal variability, which can arise, for example, due to the volcanic eruptions, which can modulate the aerosols in the stratosphere. So this was a paper that came out in 2021, which said that as climate warms up, and you have with global warming, if you are going to get these big volcanic eruptions like Pinatubo, because the tropospheric height, with climate warming, the height of the troposphere, tropopause height is going to increase. The buoyancy in the atmosphere is going to be very strong. Vertical motions are going to get stronger. So if there are these big eruptions, the stratospheric, these aerosols from the volcanic can go very deep into the stratosphere, and they can produce stronger cooling. This is what the paper said. So this is a possibility. And but large volcanic eruptions can also trigger El Niños. Several recent studies have shown that following big eruptions like the Pinatubo and the Mount Agung and so on, we can typically after a year or so, it can affect the tropical ocean atmosphere coupled system, and in a way that you tend to get a El Nino-like pattern in the sea surface temperature, and which in turn can affect the monsoon also. But the aerosols the stratospheric aerosols can also cool, and because they stay there for more than 2 years, and they can reduce the incoming solar radiation by scattering the incoming solar radiation. And so they can also have an impact on the monsoon directly by affecting the land-sea contrast. And so the question is, there was an interesting paper by Marwan and Kurt in 2005, when Krishna Kumar's paper in Science, they talked about this ENSO monsoon correlation has been weakening in recent times. And this was an interesting study. They showed that when you talk about this weakening relationship between ENSO and monsoon, two big climatic systems, they said we should not just look at the correlations. We should also look at because these are oscillatory systems. They considered them as oscillatory systems. We should also look at the phase difference of these oscillations. And they came out with a novel idea of how to look at the phases of the ENSO oscillation and phases of the Indian monsoon oscillatory system from data. And they plotted, this is a kind of a phase difference between the Nino 3 index and the Indian monsoon oscillatory systems. And this is shown in time. And what you find is, and what is shown on the bottom is the volcanic eruptions, the radiative forcing. And this was the big eruption, the Krakatoa. And you have this El Chichon, this is Mount Agung, this is the El Chichon and the Pinatubo. What they find is, these are the periods when you see this phase difference is almost constant. That means it's a kind, they are synchronized. The ENSO and the Indian monsoon oscillations are synchronized. Their phase difference is very small. It doesn't vary. It's constant. And interestingly, they find that these plateaus or these flat areas which have happened, all have happened immediately following large volcanic eruptions. So they proposed an interesting idea that these volcanic eruptions, because of the aerosols radiative forcing, it could bring a phase synchronization of these two oscillatory systems. So it was an interesting idea, and my student Manmeet, who is now a scientist also at IITM, I told we should look into this problem. We have this IITM Earth system model, and we also know how to introduce volcanic eruptions in the model. And can we test this hypothesis? And so this was a paper where we could fingerprint the volcanic effect of the volcanic forcing on the ENSO and Indian monsoon coupling. And we did several large ensemble simulations for the Krakatoa eruptions, which happened in the 1883 or so. And what we find is typically a year, and we started with different initial conditions, neutral initial condition, a warm state like the ENSO, and the cold state like a La Nina. And we did several model experiments, also analyzed paleoclimatic data and several records, and also several, one of the simulations from the IPSL model, which was for the pre-industrial, which was typically for the last millennium simulations. All of them, they showed that they provided strong support that indeed volcanic eruptions can provide a kind of a mechanism for the phase synchronization of the ENSO and the monsoon oscillation. And I'm not going into those details. So volcanoes can be a very important driver. So in the future, in the near future, as an internal source of internal variability, it can affect the monsoon precipitation through these very complex links. Also, I'll just briefly touch upon the intraannual and decadal variations in the monsoon. We don't know how the ENSO is going to change in the future. In the AR5, it was assessed that with a warming climate, as the climate warms, we will be getting more into a El Nino type of climate, more warming-like pattern in the eastern and central Pacific, and the Walker circulation will weaken because of the increased water vapor compared to in the atmosphere compared to the precipitation. The Walker circulation will weaken, and we will be getting into a more El Nino-like pattern. But now recently, some studies have kind of countered this argument. Especially, they are saying that although the CMIP5 models showed this, now the observations in the last 50, 60 years, they show that in fact the Walker circulation has actually strengthened, and that we are having long Pacific decadal oscillations, like a long extended La Ninas. And there are problems in the CMIP models, especially the representation of clouds in the Eastern Pacific. This morning, we had a very nice talk by Dr. Vivekananda. So the representation of cloud process, because of these biases, what will happen to the ENSO, how it is going to change in the future in a warming climate, remains an open question. And this is also another paper, the Vinju Chai et al. With Ashok and other people. They're telling that in the future, the IOD can also become stronger. We can expect stronger Indian Ocean dipole. This is something important because, as I said, the monsoon rainfall, which we are over our region, can be influenced by IOD. The question is, if IOD events are going to become stronger, what it means for the Indian monsoon. So lastly, I will touch upon the prediction of heavy rainfall events in a changing climate. Not only yesterday also I made this talk in one of the other meetings in the Indian Express meeting. This was one paper by Professor Goswami in Science. From the IMD data, they showed this very heavy rainfall over central India. The frequency count has been increasing. Also, heavy rainfall more than 100 millimeter per day, whereas the low and moderate rains have decreased. So this frequency of heavy extreme rains are becoming with warming. That's one of the signals of the greenhouse gas warming, global warming. And this was also substantiated in a subsequent study by Raghavan et al. With the longer term data that these extreme rainfall events are increasing and they are linked to the sea surface temperature over the Indian Ocean, which is also warming. And we also see that from the models, this was in one of our earlier papers, we used a high resolution model because to capture the heavy rain event, second order moment, you need this high resolution to capture them, extreme events. What we find over the same region over central India, rainfall thresholds more than 100 millimeter per day, you are able to get in the model which has the greenhouse gas forcing and the other anthropogenic drivers, but not the blue line, not the natural run. And the black line is the observed rainfall, extreme rainfall events. So clearly, I think for the heavy rainfall events, more than these intense events that we're seeing, the statistics of those events, they seem to be related to the global warming. And this was also assessed in the IPCC report that with the warmer extremes, temperature extremes are also going to increase over land. Likewise, the heavy precipitation extremes are also going to increase as with every additional half degree warming in the global warming, we are going to see discernible changes in the precipitation and temperature extremes globally. And this is mainly because of the increase in the water vapor in the atmosphere. The water holding capacity increases because there's a temperature dependence of the saturation vapor pressure. With more temperature, more evaporation, both from the land and ocean, and the water holding capacity as it increases something like 7% per degree warming. And also the heavy precipitation increases also at the same rate, just like the water vapor increase. And so a direct consequence of the water vapor increase is the increase in the heavy precipitation. But when we talk about heavy precipitation, which we are seeing now, many places in India keep getting a lot of heavy rainfall. They are also dependent on circulation, not just the thermodynamic increases. It's much more complex. Like we had this big event in Uttarakhand in 2013, which was an interaction because a low pressure system from the Bay of Bengal moved quickly into the Kedarnath region. There was also a very deep meridional trough extending from the extratropics, from the polar regions in the upper atmosphere, in the mid-tropospheric levels, and the convergence of these two systems. So the anticyclone, Tibetan anticyclone became very, very strong, very unstable. At the same time, you had this deep trough from the extratropics, which interacted with the monsoon synoptic system and triggered this heavy rainfall over India. So how to produce, whether these in climate change, what will happen as it warms up with increasing moisture levels in the atmosphere, these type of events. And this picture also shows the deep extratropical trough and also the low pressure system. These are on isentropic surfaces. So this is an important problem with climate change, how it is going, these precipitation events are going to change, because already the rainfall during 2030, many of these areas received one-day rainfall was more than 300, 400 millimeters. So clearly that's an important problem. And also over Gujarat, we had, I'll also briefly touch upon this heavy precipitation that can happen because of these mid-tropospheric cyclones. Many places in Gujarat and coastal areas of Maharashtra, Surat, and many areas, they can get rainfall in just 2-3 days, more than 700, 600 millimeters, and this leads to massive flooding. And these cyclones, we have a good understanding because thanks to the TRIM heating data, and we are able to understand what are the type of cloud systems and why these mid-level vortices form. And typically these events happen when we have this organized convection moving northward, the ITCs are moving northward, and these MCS, mesoscale convective systems, can produce this type of MTCs, tropospheric cyclones. And also there was a earlier paper by Dar et al. Of one of the most severe rainstorms of India in 1984, which was due to a low pressure system that formed in the bay and moved westward. You can show that, see that this typically led to heavy flooding over Surat and Mumbai, Navsari, and Dharampur. In 3 days, it received more than 1,500 millimeters of rain. So clearly, many of these events were associated with IOD events, positive IOD events. I'm not going into the detail, and the duration of these events are becoming longer. So as these events are becoming longer, we did this study recently, and it turns out that many of these long-lived events, heavy precipitation, are associated with the IOD type of positive IOD, which channels this moisture from the Eastern Indian Ocean towards this region and causes this heavy rainfall. And once the rainfall continues for many days, can lead to flooding. And also with climate change, as the land gets heated, the Tibetan Plateau and some of these areas, and you can have changes in the diurnal convection activity. And this is a typical example of a Leh flash floods that happened in 2010, immediately after the Pakistan floods. This place, Leh, which is actually, it's a very dry, it's a dry location. It's a high altitude cold desert, and 3,500 meters above the sea level. And this happened because of torrential rains that were delivered by a succession of mesoscale convective systems. And this was a paper by Rasmussen and House, because as the land gets heated during the day, and you have moisture coming from the Bay of Bengal and other from the Indian region, once it is transported to this region, these mesoscale systems that form during the daytime, they move westward and they can produce heavy rainfall. So this is just a schematic of these diurnally generated convective cells over the Tibetan Plateau in the context of persistent 500 millibar pattern directing the MCS overlay, forcing moisture over the slope of Himalayas in the region. So in short, I want to say that monsoon variability change, and so these are very, very important things we have to keep. And it's a multi-scale interactive phenomena. And when we are talking about the prospects for improving the monsoon predictive capabilities in a changing climate, we have to reduce the uncertainties in the monsoon projections. We have to also develop a framework based on global energy constraints and regional monsoon complexities. Each regional monsoon has its own complexities. So while we understand energy from a global energy constraints like the greenhouse gas or the aerosols, we have to also understand the complexity of the regional monsoon. And that framework is going to be very, very important. And we also have to improve the physical processes in the models, organized convection, latent heating, warm rains, which are very common over especially the Western Ghats, orographic precipitation, mid-level circulation, aerosol and cloud interaction, and so on. And also these large-scale sea surface temperature gradients, they are very important, like the ENSO and IOD. They are fundamental for regulating the tropical and regional monsoon precipitation, because they are the ones that are going to alter the moisture and heat fluxes, the convective activity, and it is for the mean, variability, and extremes, all of them. And in addition to the model developments, now there are several innovative techniques like the AML and deep learning techniques, which may be important, because when you're talking about extreme precipitation locally, models cannot, despite very high resolution, we may not be able to do that. So we may have to rely on these empirical methods where there is substantial amount of data. And in short, I think we need to have a process and predictive understanding by combining observations and for advancing our predictive understanding of the coupled system, ocean observing system, atmospheric observing system, data assimilation, and model predictions. Yeah. So, and development of the early warning systems. So with this, I want to end my talk. Dhanyavad, Jai Hind.
Thank you, sir. Thank you so much for such a wonderful, nice, and very informative talk.
Thank you.
I'm sure everybody would have enjoyed as I enjoyed.
So shall I stop sharing?
Maybe yes. So now it is the time of question answer.
Yeah.
So what I'm going to do that I will request all the audience to raise their hand, and I will directly ask the question. And if they have any problem in directly asking, they can type the question and we will read it out. So, yes. Okay, so I can see the name.
Between there was some interruptions. My phone kept ringing and some fellow.
That's okay, sir. That's fine. It happens.
Yeah.
In online thing, it happens.
Oh, yeah.
Okay, so I can see the hand raised by Abhijit Chatterjee. Abhijit, please go ahead.
Yeah, hello, sir. Can you hear me?
Yes, Abhijit. Yeah.
Oh, thank you very much, sir. This is Abhijit from Bosch Institute.
Hi.
So,
Hi.
for your wonderful presentation. Sir, I have a question that I was looking at a report a few days back published by the Australian Bureau of Meteorology. And they said that for currently the IOD, Indian Ocean Dipole, is neutral. Okay. So still we are having a more or less, I mean, quote unquote, normal monsoon. And so my question is a kind of a fundamental questions is that does the aerosol forcing or greenhouse gases forcing or the effect of aerosol and greenhouse gases have the ability to offset the large scale ocean atmosphere coupling system? I mean, when Indian Ocean Dipole is neutral, still we are getting a normal kind of monsoon. Maybe the type of rain may differ. Because what I have seen from the various reports and I have analyzed that shorter duration, heavier rain is increasing rather than the longer duration light rain. So what's your view on that, sir? I mean, how the aerosol and greenhouse gases forcing can overwhelm this large Indian Ocean Dipole kind of ocean atmosphere system?
Yeah.
Thank you, sir.
Yeah, it's a good question. Actually, if you see, when from my mind, I'm trying to recollect. Before June 15th, actually the situation was looking very bad, the monsoon situation in the country. And it was almost minus 49, minus 50% deficient. Of course, monsoon would not have advanced. I understand that. The situation was very grim. Actually, the air was, there was a large-scale subsidence over much of the subcontinent. Things were looking pretty bad. Now, and later on, I think in the later part, I think some cyclone developed, this Biparjoy, I don't know when it happened. That moved northward and it produced a lot of rainfall, and it also entered northwest India. And that was the time when there's a moistening that happened in both the Indian region, and the trough also, the monsoon trough also slowly started picking, and the low-level flow started picking up. And so the El Nino was going on. People were really concerned that this is going to be a big, so monsoon may be badly affected. But then slowly, one after one, I see once the monsoon heat source develops and a depression forms, then the trough gets stronger. And the earlier heavy rainfall that happened over Punjab and North. So it was also interaction of this very a strong monsoon trough with a mid-latitude trough in the mid-latitude westerly, something like the Uttarakhand type of event. So in general, the monsoon trough has also been pretty active. Now, and then this cold anomalies, I started now slowly picking up. So you're right, the IOD is right. Now it is neutral, we cannot say. But it is also providing an opportunity, and the cold SSTs are there. Convection is not developing in the Eastern Indian Ocean. So you have a high pressure sitting there. So once you have an anomalous high pressure sitting in the Eastern Indian Ocean, you are going to have more outflow of the moisture from that region. So which can enter into your low level flow, and which can feed this convective activity over India. So in this situation now, I don't know how aerosols can, because it's already precipitating so much. So all the aerosols are going to be washed out. If at all, maybe some parts over the eastern UP, Bihar, where things are dry, maybe locally there could be aerosols. And greenhouse gases, and if there is a warming because of the GHG, as I said, the water vapor is going to increase, and water vapor being a greenhouse gas by itself is also going to increase the warming and heating. So it is going to further increase the precipitation. So in a way, let us see, my hope is that the IOD may strengthen in the coming days and months. And also the monsoon will be strong. That is my feeling. So it is, so these are highly interactive. Yeah. You're right. I think these anthropogenic drivers are there. Also, these modes of variability are there. So they're all interacting, and you have these synoptic scale systems and in the low pressure systems and the monsoon depression and so on.
Yes,
So it's all a complex mix that is going on.
Yeah, so I see some more hands. So I would request now Professor B.B. Rao to ask the question. Professor Rao.
Hear me, please.
Yes, you are audible. Yeah.
Okay. Dr. Krishnan, it is a wonderful talk and very, very informative. And what I want to make a comment rather than a question.
Okay,
It's
sir.
like this. In the case of middle and high latitude, the variability in the zonal direction in space is almost very less compared to what it is in the tropics. What I'm saying is, in the case of middle and high latitude, it is essentially long Rossby waves that dominate both weather and climate. In the
Correct.
case of tropics, the variability both in space and also with season is very high. What I'm saying is, even in the case of India, for example, Indian monsoon, the four seasons, we say pre-monsoon, monsoon, winter, and summer, if you take, each season is different. And what I am stressing is, instead of using these very complex, highly nonlinear models,
Yes,
we
sir.
have to make individual simple systems to understand the
Yeah.
physics of the problem. For
Correct.
example, in the case of the tropics, unlike in the middle latitude, the interaction between the cloud scale and the large scale is very, very important. Most of the energy, even for the synoptic system, which cause rainfall, is essentially given by the latitude release in cumulus convection scale. And so, unlike in other tropical oceans like Atlantic and Pacific, over North Indian Ocean, we don't have much studies about the parameterization of the convection. And this parameterization convection, I think, is very important, and it varies season to season from one region to another region. And in these models, if you want to improve the credibility and the utility of these models, you have to make some simple, what you call, studies of understanding the basic dynamics. Thank you very much. It's a wonderful talk. Thank you very much.
Thank you, sir. I agree with you, sir, completely.
Thank you, Professor Rao. Now, Shani Tiwari. He's from NIU Goa. Shani.
Hello, can you hear me, sir?
Yes,
Yeah, you are audible.
yes, Dr. Sir.
So, thank you, sir, for wonderful talk. I just need a query regarding to that. As you told that in a southern hemisphere, if global warming concerned, it is going to be the reduction in precipitation, as per your few slides somewhere. So, as per sir, black carbon or some absorbing aerosol like dust or black carbons, they have potential to increase the rain intensity. So whether the rain intensity have capable to offset the global precipitations, and if yes, then up to what scale? Because in southern hemisphere, Sahara deserts and African region especially has the largest contribution in absorbing aerosol. So I just want to comment on your comment on this.
Yeah. So, Dr. Shani, I think what I was showing was mostly the effect of because mostly that is the sulfate emissions. What I showed was in the northern hemisphere, it has dominated. So there is more cooling in the northern hemisphere compared to the south. And the south is continuously exposed to more global warming compared to the northern hemisphere. So because of this interhemispheric asymmetry, there will be more rainfall to the south of the equator. That's what I was trying to say. So compared to the areas in the north, that's what was that picture was showing. But okay, so so you are asking the question, what is the role of the absorbing type of aerosols? So
Yeah.
what in our own, I did not show that slide here. We had done an experiment where we have emissions, many of these emissions over the Asian region. This was based on the CMIP-6 data set, the optical properties that were given to us. And so when we looked at it, it had a lot of absorbing type of aerosols, because when we looked at the heating due to the, so in the lower level, there was more increased stability, absorption in the lower troposphere, and also a reduction in the stronger reduction in the radiation at the surface compared to the top of the atmosphere. So there was a net absorption in the lower troposphere, very similar to the absorbing aerosols. And what we found was once this type of absorbing aerosols are there in the model, and you have also global warming, the monsoon, because of the increased stability, the winds will weaken, the tropical circulation will weaken. And that again reduces the evaporation from the, because the wind speed, if you decrease, the evaporation from the Indian Ocean and from the Arabian Sea is going to decrease, and the moisture convergence is going to decrease. That will lead to further reduction in the rainfall. So the increase of stability due to the absorbing aerosols in the lower level, its effect on the circulation will be very strong. So if that weakens the circulation, precipitation is going to decrease. So that is what is our take on that. Maybe I can share that paper with you.
Yes, sir.
Okay,
Thank
sir.
you.
Thank you.
And the next person who is in queue is Dr. Bharat. Dr. Bharat, would like to ask directly?
Hello, sir.
Yeah.
Can you hear me?
Yeah.
Yeah, so actually I'm a PhD student, sir, not a doctor.
Okay, you will become doctor. Continue your question.
Thank you. Okay, sir. So actually, my doubt is that Sir was talking about the role of anthropogenic aerosols and greenhouse gases in the in the precipitations and the climate indices and these things and all. Like when we take the extreme cases, would that be appropriate work with the climate models, or would it be like better to go with downscaling for the study of extreme events, particularly in south and eastern parts of Asia? Downscaling would be like appropriate way to do that, or else we have to look in other ways. That's my
Yeah, I think some people are using downscaling regional models. They take the lateral boundary conditions from these global models, and drive the regional models. But again, it depends on, getting this very heavy rainfall is proving to be very, very difficult. It's what, no matter, even if you increase the resolution, it's going to be, it's a challenging issue. But I think if it's a reasonable, like if it's an amount like over a large area of central India, 150 millimeters per day number of count, still it may be possible. If you have a reasonably good model, we'll be able to do it. But these very, very extreme events that we are seeing over a small place, that is, models are having a tough time even now. I mean, even the global model, which we are running at 12.5 kilometers or 6 kilometers from IMD, it is a challenge for them.
Okay.
So, okay. So, okay, sir.
Yeah, okay, Bharat. Yeah,
Okay,
we have other people also. Okay.
Yeah,
So, Dr. Shubha Verma, you would like to ask?
Okay, thank you, Dr. Neeraj. Krishnan sir, thank you very much for a very insightful talk. It has been a great learning listening your talk. Sir, I want to get further insights from you on when we look at the IMD rainfall data for a long term, then we always see the modulations, the spatial changes, like the spatial weakening trend, as well as the strengthening trend of the rainfall. Then do you think that this the circulations, whether it is created for ENSO or La Nina, whatever, so is this driving these spatial modulations? Because these spatial modulations are always seen whether it is IOD positive, IOD negative, or it is La Nina or El Nino year. So may I know if it is governed also by the aerosol radiative effects, spatial variation of it, which we have not yet explored properly in the models, because our burden in the models in terms of species distribution, because anthropogenic or dust may have a different kind of radiative effects, which may be impacting the spatial modulation. So what is the, may I get your insight how to explore this part?
Yeah.
Thank you, sir.
Yeah, thank you, Dr. Shubha Verma. I think you have raised a very, very good point. Yeah, so at least what we are seeing from the IPCC assessment and from some of our studies and other studies, the effect of aerosols on precipitation is, if you make changes in the radiation due to the aerosols, by changing the scattering and absorption, it has an effect on the precipitation over the tropics and over the monsoon. That is clearly seen because that radiative forcing is substantial. Now there are indirect effects due to the formation of the clouds. That is a highly uncertain area still. The cloud aerosol interaction and how it produces the precipitation. That topic, our understanding is, and in fact, the AR6 also has an assessment. There's a box. In fact, Professor Daniel Rosenfeld wrote this box. So the radiative effect due to the aerosols, their influence on precipitation is kind of very, I think the understanding is much better compared to the indirect effects. That is number one. And as you said, these variabilities like El Nino or IOD, they kind of overwhelm when we talk on regional timescales. So, but there must be definitely ways to separate them. So how to separate the effect of the aerosol forcing and the greenhouse gas forcing compared to these indirect, all these internal variabilities. I'm sure that there must be clever ways to do that. But that's going to be a challenging problem. But however,
okay, sir. Thank you.
I don't know whether I answered you properly, but that's
no,
it.
Sir,
but you're asking a tough question, basically.
Yes,
Okay.
Thank you, sir. Thank you.
Thank you, sir. Now, Dr. Pandit Roy had raised the hand twice, but he has lowered. So I'm not sure whether he would like to ask or not.
Okay. Thank you, Dr. Neeraj, and thank you, Dr. Krishnan, for a very informative and excellent presentation. And you covered a wide variety of influence of aerosols. Especially, I think you mentioned about the volcanic eruptions, how volcanic eruptions also adds to this, play a role in El Nino. Earlier we used to see that the El Nino will lead to a drought year, and because of less precipitations, the aerosols were observed to be high. So now that we are seeing that the volcanic aerosols itself play a role in the formation of El Nino.
It can.
It's a very interesting phenomena. I'm not. It's interesting to hear. Maybe I have to go through all these papers. I don't have any questions directly, but it's also you gave that Walker circulation is decaying, and I think we also looked at earlier. Sanap showed Hadley circulation was weakening. So in turn, the aerosols are weakening the monsoon circulation. At the same time, the heavy precipitation events are increasing. So
Thank you, Dr. Pandey. I think experts like aerosol experts like Dr. Pandey, Dr. Devra, and all, they have done a lot of work on these things, on aerosols especially. And so these proving to be these big eruptions, I think they are affecting. That's what. But as I said, internal variability always dominates. So how to take out that is the key. Okay. And but if we can, many studies are showing that typically after this Honga Tonga also there was a big eruption about a year back. Yeah. Mm-hmm. And and interestingly now some studies are showing that it also introduced water vapor in the UTLS, huge amount of water vapor. Mm-hmm. And water vapor being a greenhouse gas, some people are interested to look at the Honga Tonga eruption. So that there's a great emphasis on that now. So So we really need to, because it is not, see, once you start influencing big drivers like El Nino, Enso, then I think it's something we need to really think how it is going to affect the monsoon. So all these, they're all interacting, the natural variabilities and these aerosols and greenhouse gases, volcanoes. So I think this field is going to be very, very interesting. That's what I think. It's going to be throw up a lot of opportunities in the future.
Yeah, right. Thank you very much.
Thank you very much.
Okay, thank you, sir. Our next
Thank
person, Professor Devara, you are.
Okay. Good evening, everybody.
Good
once
evening,
again.
sir. Good evening so much. Nice to see you, sir.
At the outset, I wanted to congratulate Dr. Krishnan for his excellent and path-breaking lecture, as always.
Sir,
Of course, I have been hearing his mastership over many variety of models. Still, I regard the model Earth system model, of course, which he drives and then controls and commands very much. But you see, I wanted to have one suggestion from him instead of asking question or making further discussions. Many aspects he discussed already. Of course, variability, I also agree. But you see, how do you prescribe the aerosol in any of the models you talked about? Because it is a long-aged problem. This aerosol precipitation cycling or linkages, very old problem, and then even now also there is no clear-cut idea. What type of aerosol you are talking? One side about the greenhouse gases, one side about aerosols. Of course, I think that greenhouse gas again is an aerosol. When you talk about the gas to particle conversion process, some of the greenhouse gases, they don't remain as gas, they become particle. So what parameter? Aerosols have variety of characteristics. So which characteristic of aerosol, if you consider in the model, will it give near right answer to our precipitation aerosol linkages?
Okay.
Because variety of mainly grossly, if you see radiative forcing, people say, okay, let us take radiative forcing of variety of aerosols. Different aerosols are different. Somebody was talking about the black carbon aerosol. That is also very important. Of course, radiative forcings are different for different type of aerosols. But what type of aerosol, what property of aerosol, Dr. Krishnan, you would like to suggest for all the modelers as well as the experimentalists to come near to the relationship between aerosol and precipitation?
Okay, sir. Sir, you put me in a very tight corner.
No, this is you are a reasonable person to answer this, because this is the main.
I think that's a very good question. Actually, now the problem earlier, what people used to start from emission is they start with the emission inventory.
Right.
And they say these different types of aerosols are there. I have black carbon, I have maybe sulfate emissions, I have nitrate emissions. So put the emission sources, and then we have to get the concentration in the atmospheric concentrations. So they have to be lifted up. So it's going to depend on the surface, whether the soil is dry or wet, and depend on surface characteristics, the boundary layer characteristics, the convection in the model. So because this has to be lifted into the atmosphere first and get the concentration. And then this has to interact with all the radiative atmospheric radiation, and it's going to then change the optical properties. So at different levels, starting at the emission level itself, emission inventory itself, there are many uncertainties. And then the models, how they are going to lift this aerosol from the surface to the atmosphere, lower troposphere, or above the boundary layer. There is an uncertainty we are introducing. And then how it is going to interact with the radiation, because you may have clouds, you may not have clouds. So we are adding a third degree of complexity. And already the problem is now, so CMIP6 came out with a very smart way, I would say. And now this is only about the direct effects. Now, if you go into indirect effect, it's another level of complexity. So the problem, the idea of the IPCC or the CMIP is to come with some kind of a uniform assessment it may not be complete by any chance. But so we have an understanding, some understanding of the greenhouse gases. Do we understand the effect of the aerosols? This is what, and what is the assessment, how it is going to affect the climate. So when they say it has, if I have only aerosols due to the sulfate, the temperatures would have been globally by 0.4 degrees. That's a very robust assessment. So it is based, because multiple models, all the groups, they do the same experiment, and they come out with this conclusion. So the confidence statement, the reliability has to come based on this consensus idea. So with this idea, CMIP 6, for the first time, I think Bjorn Stevens, he recognized this problem. I think they came out with a group, with a data set known as MAC V2SP, a simple plume model. So they had the satellite AODs for the year 2005, and some in situ observations were there. And based on that, and they also had some information of emissions in the past from different locations. So they came out with a statistical method, and going by the different seasons, they came out with the optical properties, the AOD, single scattering albedo, and asymmetry parameter for different wavelengths. They prescribed it for the historical period and the future. And all the groups, and it was validated for some of the recent period, 2005, with the satellite data. And they said this data set can be used by all the modeling groups. And so now all the modeling groups use this for that. And by and large, it satisfies some of the large constraints, as I was showing that GBA data set, the radiation decrease and those type of things. And so when you apply, because we know with the greenhouse gas, how much radiative forcing, how much we have added because of the carbon dioxide, methane. And so we have added maybe more than close to 3 watts per meter squared or more. And now how much is aerosol offsetting? So that we want to get. How much is the reduction in the shortwave radiation by aerosol? To get a handle of that, I think we need to do this first. And maybe I'm sure it will get improvised maybe in the CMIP 7. And they also have a parameter for the indirect effect. They call it as the TUMI parameter, mainly by changing the radiation, the cloud albedo properties because of the TUMI effect, because of the air pollution. Of course, we did not switch on in our model, but that is also possible. So in a very rough extent, we can get an estimate of the indirect effect of the TUMI effect due to the aerosol. But mostly it is dominated by the direct effects, direct radiative effect. And I think they have done a pretty good job, I would say, for at least making these global assessments and coming out also on a regional scale. Now, when we get into the details of, about the black carbon and other aerosols, which are varying spatially and temporally, they have such a large variation. How to account for them? That's a big challenge. And hopefully let us so the CMIP is a very good exercise where they can set the protocols, where they can set that all the groups you have to do this. So, and once you become part of that group, you follow that, and that is one way to get the job going on.
But sorry for the interruption.
Yes, sir.
You see, you have talked about the gross parameters which characterize the aerosol, like optical depth, SSA, and all. But I just wanted to know from you, because you have worked with numerous modelers, and then you yourself have involved, whether anybody, anywhere, any model, a parameter called refractive index of aerosol, anybody has used, because it is an answer for both scattering and absorption.
Yes, sir. Yeah. So, yeah, maybe you're right. We can look into this. We can look into it definitely. So, but right now, the way it is that the optical properties are very important when it comes to climate. If you want to understand the climate, how these things are affecting the radiative fluxes, optical properties are very important, aerosol optical properties.
Yeah.
That is the overall recognition. Maybe when it goes to health, the size of the particle becomes important. Then it's a different story.
Yeah.
Okay.
Okay, sir.
Thank you so much.
Thank you,
so much.
sir. Thank you
Okay,
so
sir. If you don't mind, if we have some time, there are some questions in chat box also. Can I read them?
Yes, sir. Sure.
Okay. And before that, can I also ask a question?
Yes, of course.
Yeah.
If I know, I will answer. Otherwise,
I hope it is not a foolish question.
No, you can ask. Yeah.
So you talked about aerosol and this moisture interaction, and you were talking about on a big scale, means on the hemispheric level and all. But if we go on micro scale, for example, a few kilometers only, say there are too much of moisture and it is passing over Mumbai, which is a metropolitan city or mega city. Then there is a huge amount of aerosol which are coming from urban aerosol which are coming. So in a way, they can inject particles like cloud seeding. We know about the cloud seeding. So similar way, naturally, urban aerosol getting injected into clouds, and they are affecting them. Suddenly there is a huge rain, or they can dissipate or precipitate depending upon the size or composition, depending on their hygroscopicity or they are hydrophobic or hydrophilic, or depending upon those things. So are there any studies on which people talk about on micro scale how aerosol can affect?
There was one paper that came in Science. They talked about how these aerosols can invigorate clouds. Okay, how to parameterize in this model. And because some of these aerosols can also, as you said, hygroscopic aerosols, they can invigorate and lead to very deep clouds, deep convective clouds. And they can produce heavy precipitation. So, and this was by, I don't remember some name. It starts with C, Cronin or something. It came in Abbott and Cronin or something. It came in Science. It was an interesting paper. They had done with a regional model. So I agree. If you want to do this regional, one is from a climate angle, we have to really look at how this is going to change the radiation, how it is going to change the climate, and then of course we see how it is going to affect the monsoons and precipitation. But the other thing is, when we are looking at process on a small scale, on a regional scale, what is the effect of these different aerosols and different types of heavy precipitation or low precipitation? That needs a different type of assessment. But it is, I don't know who has done, but this Cronin and Abbott is a good paper. That's what I would say about this cloud invigoration by the aerosols.
Okay, thank you. So now let me ask a few questions which are in the chat box. So Dr. Kriparam from BHU, he has written a question, but I think it is similar to what has been asked by Dr. Shani Tiwari. So Kriparam, if you are around and if you feel that whatever Shani has asked was different than this, please raise your hand. I will move to the next question. Okay, it is by Archana. And she's asking, the CMIP future assessment shows the increase in rainfall. This increase in rainfall in terms of cumulative rainfall or extreme rainfall? This is her question.
Okay. Both, because extreme, definitely it is going to increase. The temperature increase, water vapor increase, extreme is going to increase for sure. But mean also is going to increase in many areas, but some areas are going to get drier also. Some of the subtropical areas and things which I showed earlier.
Then Ankita wrote that, sir, how aerosol density is related to the precipitation? Is there any relation?
I don't know, but maybe because we talk about the optical properties, as I said earlier, which is what we have done. And these experiments, I think people have to do and see. Because on regional scale, if you start adding more complexity, the question is also going to become more and more complex. So answer is going to be challenging. So
yeah, okay. So another question is by Anand Srinivasan. Thank you for the interesting and informative lecture. A general question is, how does climate change will affect Indian monsoon in the future?
Yeah, in the future, as I said, with more warming, more increased precipitation. So monsoon precipitation will increase in the future, mid-term and long term. In the near term, it will be affected by internal variability also.
That is what we are feeling right now. There is so much rain.
Yeah.
Another question is by Mr. Dhananjay Trivedi. My question is regarding especially this year 2023. Why this year we feel so much heat waves and extreme precipitation over India? These questions are from YouTube. People are watching on YouTube also.
Yeah, heat wave is, you can have, if you have, it's also circulation dependence, heat wave conditions. If you have a lot of sinking motion and, soil becomes very dry conditions, they can all increase your heat wave conditions also. And in addition to, of course, the global warming is happening, but it is circulation dependent, and it is also dependent on the soil moisture. One of our colleagues that showed this role of soil moisture on the temperature extremes and things. Yeah.
Okay. So others are appreciation for your talk mostly. So I will not go through them. So with this, now we are coming to the end of this event.
Yeah.
This is vote of thanks, and it is my present duty to give vote of thanks.
Thank you, Dr. Neeraj.
Yeah. So firstly, on behalf of IASTA and on my own behalf, I wish to thank Dr. R. Krishnan for kindly accepting our invitation to deliver this wonderful lecture. Everybody will agree that it was very informative. As a director, we all know that he is a very busy person, and there were many events lined up. Some ministers were visiting, and Foundation Day of IITM is there, but still he kept my words. He took out time and he is giving the lecture. So for that, thank you very much. And I also wish to thank the efforts of BARC team led by Dr. Manish Joshi, who is doing a great job in every lecture, from making flyer to execution of this online event. They are doing a wonderful job. And lastly, I wish to thank the whole IASTA team led by Professor S.N. Tripathi for their continuous support. And with these few words, thank you all. Thank you very much. And we will come again next month with some lecture by another Indian scientist. Thank you very much.
Thank you, Dr. Neeraj.
Thank you very much.
Actually, I'm repeating many slides. I don't know, people may be getting bored also.
No, sir. It was very informative indeed.
Okay,
sir. Thank you.
Thank you so much.
Thank you.
Thank you.
Thank you.
Thank you all.
If we can stop the recording now. Yeah.